Okay, so good morning, everyone. I forgot to bring your previous homework. It's stated I have it in my office, but I just forgot to bring it. So after the class, if any of you would like to stop by my office and...
We can wait if you were getting it.
Yeah, sure. So maybe after the class, if any of you would stop by my office, I'll give it to him. Sorry to forget to bring it to the class. So today we're going to continue our discussion of the shear, just solving examples, the theory, okay, the equations that we used, everything, we're done with that. We're just solving more and more examples, okay? So today we're going to go ahead and solve example 8.3. So for example 8.3, we have a beam, okay? That beam to be, I'm just drawing its section to make sure that you realize the dimensions. So it's supported by a column here, and the clear span here is 14 feet exactly, okay? This beam is made out of reinforced concrete. FC prime for the concrete is 4,000 psi. F yield for the steel reinforcement is 60 ksi for all the steel, the longitudinal and the transverse. Transverse, what I mean by transverse, it's the stirrups, okay? It's transverse steel. And the load applied on this beam, the dead load, there is a uniform load of 4 kips per foot, and the live load of 6 kips per foot. Okay, we're required to select number 3 U-shaped stirrups for the beam shown. Okay, so when we're talking about stirrups, that means you have to design it for shear. Okay, stirrups are the things that resist the shear. When we take cross section of the beam over here, that's given as well. The cross section of the beam, it looks like this. It's a rectangular, simply a rectangular section. The width is 15 inches, and here we have 4 number 10 bars, okay, and the depth is 22.5 inches, and the cover is 2.5 inches. So that's our section, okay? We need to design this beam for the shear, okay? So how to design it for the shear? So you remember our design problem, right? When we wrote the summary for a design problem, what are the given things? I'm just going up here. For a summary for this design problem, you have FC prime, F yield, VD, V ultimate. What of those do you actually have in our design problem here? You have V and D, the dimensions of the section, F yield, FC prime. What about VU? You have to calculate this yourself. How? Doing structural analysis. For the structural analysis here, this is the simplest beam. It's a simple beam. But let's say you have a large structure. Just run structural analysis, okay? Put it on the stat software, put the dead load, the live load, run the load combinations, and find V ultimate at the section that you want, okay? At the end, when you graduate, you're not gonna, usually have a simple beam like this, okay? You're gonna have a complicated structure, okay? But how to find V ultimate for that complicated structure, you learned that in structural analysis already, structural analysis 1, structural analysis 2, okay? So right now I'm not complicating the way you find V ultimate, but in real life, finding V ultimate is more complicated than this, okay? So how would we find V ultimates? Through structural analysis, right? First, we need to apply the load combinations, okay, and do some structural analysis. Our beam looks like what? This is our beam here. It's a simply supported beam. What load do we have on our beam? This is 14 feet. I have to analyze my beam for the maximum load combination, which is 1.2 times the dead load plus 1.6 multiplied by the life load. So 1.2 times the dead load, how much is the dead load? 4 kips per foot plus 1.6 multiplied by the life load, which is 6 kips per foot. So the ultimate load is 14.4 kips per foot. So now I just have to do an analysis for this simple beam with that simple uniform load, 14.4 kips per foot. How much is the maximum shear? You have to draw the shear force diagram. How does the shear force diagram look like? This is the action, this is the action. How much those gonna be? WL divided by 2, so 14.4 times 14 divided by 2, so that's equal to 100.8 K. So that's the maximum shear here. It's going to be 0 right in the middle and negative 108 kips per kips here. And then this is your shear force diagram. So how much is V ultimate, the maximum shear? Exactly. Definitely, if you use the 108, that's not going to be like a wrong design, but you're going to put more steel required. So actually, I'm going to design it at a distance D here from the support. So I'm just going to move a distance D here. So how much is this distance from here to here? How much is this? 7 feet. So 7 feet is 7 times 12, it's 84 inches. Okay? How much is D? 22.5 inches. Okay? So you can apply, the similarity of those triangles by the ratio and find V ultimate. So V ultimate at a distance D from the support, how much would that be? 100.8 kips divided by the 84 inches, 108 divided by this distance, multiplied by this distance. How much is this distance? It's the 84 minus 22.5. 84 inches minus 22.5 inches. So that is equal to 73.8 K. So that's the value that I should design my beam for, okay? Not 100, it's just 73. So if you design it for 100, your design is going to be more safe, okay? It's going to be, you're designing for 100 while you can actually design it for 73. 20%, more than 20, like 25% decrease in the value of the shear, okay? So now, we have the ultimate that I should design my beam for. What are the steps now? Find PVC, okay, to see if you need stirrups or not, okay? So how much is PVC? It's 0.75. VC is 2 lambda square root FC prime BD. So 0.75 times 2 times lambda is 1 square root FC prime. How much was FC prime in our problem? 4 psi. So it's 4,000 psi multiplied by B, 15 inches, times D, which is 22.5 inches. So PVC is going to be in pounds, 32,000 and 18 pounds. So our maximum shear, how does it compare to this PVC? Which case you don't need stirrups at all, you need the minimum amount of stirrups, or you need to design for stirrups? Which case you have here? The ultimate is larger than PVC, right? The ultimate over here is 73.8 thousand pounds, okay? Here you have just 32,000 pounds, okay? So the shear force that is applied at the critical section over here is larger than the capacity of the concrete. So you need stirrups. I need to design for stirrups here. So since the ultimate is larger than PVC, then stirrups are needed. How much is the shear force that should be resisted by the stirrups? The difference between the applied shear force and the strength of the concrete. The applied shear force is V ultimate. You deduct the strength of the concrete and divide by phi. So that's the amount of shear force that should be resisted by the stirrups. So the shear force that should be resisted by the stirrups is, here we have 73,800 pounds minus 32,18 pounds. I'm changing everything to pound here. And divided by phi, which is 0.75. So the shear force resisted by the stirrups should be 55,709 pounds. Okay? If this is the shear force that should be resisted by the stirrups, how much is the stirrup spacing? You have the equation. Okay? That's the equation here. S, the spacing, is AV, F yield, D divided by VS. That's the required spacing for the stirrups. AV, how much is AV? I have U-shaped number 3 bars. That's what I'm using for my stirrups, okay? So U-shaped number 3, so I have 2 branches times the area of a number 3 bar, which is 0.11 inches squared, multiplied by F yield, okay, which is 60,000 psi, multiplied by D, the depth of the beam 22.5 inches, divided by VS, which is 55,709 pounds. So S is 5.33 inches. That's the required spacing for the stirrups. What else should you do? Just look on the summary that we mentioned. Once you find S, what else should you do? Yeah, you have to compare. Make sure you know that it's less than the S max. So for S max, I have 4 values. Okay. The first one, let's name this S max 1. Okay, or whatever. AV F yield divided by 0.75. Definitely you don't have to memorize this value. You just have to know where is it in the ACI code. Okay. So AVF yield divided by 0.75 square root FC prime B web. AV is 2 times 0.11 inches squared. F yield is 60,000 psi divided by 0.75 square root FC prime times B web, the 15 inches. So I have 18.55 inches. The second value is AV F yield divided by 50 B web. So again, this is the area of the stirrups, the yield stress of the steel used for the stirrups, 50 B web, the width of the web is 15 inches, so this value is 17.6 inches. Okay? That's the maximum spacing. What else do we have to compare with? There is another two values, either d divided by 2 or 24 inches, or d divided by 4 or 12 inches. Which one we're going to use? D divided by 2 or d divided by 4? How can you decide which one to compare with?
Check 4.
Exactly, I have to compare. VS, how much is VS? VS, we just calculated that. VS is 55,709 pounds. I have to compare this with 4 square root FC prime B web D. So 4 times square root 4,000 PSI multiplied by B web, which is 15 inches. D is 22.5 inches. So that is equal to 382 pounds. So VS is less than that value. What does this mean? D divided by 4. S max is D divided by 4, so I have 22. Sorry, yeah, divided by 2. 22.5 inches divided by 2, so I have 11.25 inches. Okay? And the fourth value is what? 24 inches. So my required spacing was 5.33 inches. It has to be less than any given values out of those 4 values. Is it less than all those values? Yes. So which value you're going to use? 5.33. Okay? So that's the spacing that you're going to have. What do you think about, telling the site engineer the spacing between the stairs is 5.33 inches? 5 quarter? Okay, 5. Why don't you just make it close to, round it up to an inch, okay? So round it up to an inch. So the spacing here, we have to round it up to an inch because, those people inside, you imagine they are measuring 0.33 inches, okay? No, they're not going to do that, okay? So use 5 inches spacing. Okay? Everyone is good now? This is the design, right? Anything left?
Maybe.
Yeah, maybe. What? What do you think? Okay. This design is good. So I'm going to have U-shaped, number 3 U-shaped stirrups at spacing of 5 inches. Okay? So I'm just going to come here and fill my beam with those stirrups at spacing of 5 inches. Right?
There's a spot you don't need, right?
Yes, exactly. Definitely, if you fill your beam with those stirrups at 5 inches spacing, okay, that's fine. But do you really need those stirrups everywhere in the beam? No. Why not? Because if you see here, this shear force diagram, actually, when you go closer to the middle of the beam, the shear becomes less, right? So once you move in this way, the shear becomes less, you need less and less stirrups, okay? So I'm not going to put those 5 inches everywhere, okay? So as I move from here, I just need to decrease that or increase that spacing, okay? So what I'm going to do here, definitely maybe every feet, you can change your spacing, okay? Find how much is the shear there and change the spacing, but that's not practical, okay? What we're going to do as a practical practice here, okay, is, okay, at the beginning we need 5 inches, and then I'm going to decrease this once from 5 inches to some other different spacing that I need, and then maybe decrease it again, okay? So maybe just 3 parts, 5 inches, and then another other value, and then the third value, okay? So right now, what I'm picking here, definitely you can choose a different value, okay? But I have 5 inches spacing here, and then at some point I will just move or increase that spacing from 5 to 9 inches, okay? To save some money, okay? So where, if I'm going to use a spacing of 9 inches, where should I use that spacing? That's a simple question. The answer is so silly, by the way.
In the middle half of the beam, I guess.
Okay, I'm going to provide 9 inches spacing. When would you provide 9 inches spacing? I just need some very simple answer, okay? It's so silly. What I'm going to tell you, you know, yes, you can say yes. What?
It's in the middle half.
Not the middle half, no. I mean a point. Yes.
Center.
No.
Would be like.
You're going to prove. Okay.
1/3 from the end.
No. You're going to provide 9 inches spacing when 9 inches spacing is enough. Right? If 9 inches of spacing is not enough, you cannot provide a spacing of 9 inches. Okay? Does this make sense or not? Right? So where, at what point would 9 inches spacing would be enough?
Find out from the equation, I guess.
Yeah, you find out how much shear force can be resisted if you have a 9 inches of spacing and see where is the shear value equal to that value. Then at that point you can provide those theorems. You can provide that spacing, the 9 inches spacing of theorems. Okay? So now, this is what we want to do now. Okay? For economical purpose is with you, right?
Yes.
Use 9 inches spacing at some point. Okay? Why did I choose 9 inches? If you want to choose 10 inches, that's fine. Okay? This is just, you know, it's up to you. Okay? If you want to provide, let's say, 11 inches, that's fine. Okay? So for economical purposes, I'm going to use 9 inches of spacing. Okay? So where is 9 inches? Okay? Enough. So at what location? Along the beam is spacing of 9 inches is satisfactory. So let's calculate the strength that will be provided by the beam if 9 inches of spacing is provided. The strength provided by 9 inches of spacing is V ultimate, which is the strength of the concrete, plus VVC, VVS, sorry. Okay? Strength of the concrete plus the strength of the steel. The strength of the concrete, we already calculated that before. It's 32,018 pounds plus phi 0.75. Vs is AV, F yield, D divided by S. Okay? So here I have 32 and 18 pounds plus 0.75. AV is 2 times 0.11 inches squared. F yield is 60,000 psi. D is 22.5 inches divided by the spacing. How much is the spacing? 9 inches. Okay? So that is equal to 56,768 pounds. So what does this say? When the shear is 56,768 pounds or less, 9 inches of spacing is good, right? Because that's how 9 inches of spacing can provide. If the shear is larger than this value, then 9 inches of spacing is not enough, and you're going to use the 5 inches of spacing. Okay? So now, where is the point where the shear is equal to or less than 56,768? Let's draw the shear force diagram. This is the middle of the beam. Okay? So from the support here to the middle of the beam, it's how long? It's 7 feet. So 7 times 12, that's 84 inches. Right at the column here, the shear was how much? 100.8 thousand pounds. Yeah, K. And then it goes down to 0. At the distance D here, this is 22.5 inches. The shear here was how much? 73.8. This is the value that we designed our beam for, okay? And then I'm providing spacing of 5 inches till some point where the shear, I'm looking for that point where the shear is 56.768 K. At that point, when the shear reaches this value, okay, I can provide speed-ups of 9 inches of spacing. Okay? But on the left of that point, I have to provide 5 inches of spacing because the shear is larger than the capacity of the 9 inches of spacing. Okay? So where's that point? Where's that point? So to find that point, okay, you can find it by the similarity of the triangles or through the equation of that line. That line, the equation, the shear at any point is 100.8 K minus 14.4 multiplied by the distance x. That's the distance x. Where did I get this equation from? The shear, you know, you had this in structural analysis 1, statics, you have a beam like this, the reaction here is 100.8, you take a section here at the distance x, the uniform load here, W ultimate is 14.4 K per foot, so if you take a section here, you have 100.8 and this load is 14.4x, so the shear at any point is 100.8 minus 14.4x. That's the shear here. Okay? So the shear at any point at distance x from the support is equal to 100.8 K minus 14.4 x. I'm going to equate that to the magnitude that I'm looking for, 56.768 at 9 inches spacing. V ultimate is 56.768 K, should be equal to 100.8 K minus 14.4 x. So therefore, solving for x is going to be equal to 3.058 feet. Multiplying by 12, that's 36.69 inches. So here, this distance is 36.69 inches, around 37 inches. At that point, you can use a spacing of 9 inches. Okay? Only at that point, not before that point. If you use 9 inches of spacing here, it's not enough. The shear is larger than the capacity of the 9 inches spacing. But at any point beyond that point, you're good. You can use 9 inches spacing.
So
Okay?
If you chose 11 inches, it would just be further down.
Exactly, yes. So you're going to put 5 inches more here, okay? And then at 11 inches spacing is going to be somewhere over here. At that point, you can use 11 inches spacing. Okay?
Now, if we choose a number that's a distance that doesn't fall within the first half, just lower spacing. Like we chose 15 inches.
15?
And it never went below that on the...
Okay. You cannot use 15. Why? Because d max, out of those 4 equations, one of it was d divided by 2, which is 11.25.
So that's
Okay.
the...
That's the maximum spacing you can provide, 11.25.
You just go to the next lowest one.
Yeah.
On
Okay? So 9 inches, so I'm going to have 5 inches here in those first 36 or 37 inches. In the first 37 inches, I'm going to provide a spacing of 5 inches. And then beyond 37 inches, I'm going to provide a spacing of 9 inches. Okay? Now, at what point should I provide those 9 inches of spacing everywhere here? No. We know that at some point you don't need stirrups at all. What is that point where you don't need stirrups at all?
When VBC over 2 is greater than VE.
Exactly. Okay. So let's find that point where you don't need stirrups. So what I'm gonna have here, I'm gonna have a spacing of 5 inches and then 9 inches, and then at some point I won't put stirrups at all. Okay. I'll just stop my stirrups in the middle part. Okay. So at what point no stirrups is needed? So the answer is when V ultimate is less than VVC divided by 2. How much is VVC divided by 2?
16009.
VVC was 32,000, right? 32,018, 3218 pound divided by 2, so it's 16,008 pounds. 9, yeah, okay. So when the shear force is equal to 16.009 K, you don't need stirrups. Where's that point? I have that point somewhere over here. 16.009 pounds. Where's that point? So here, I've divided my beam into 3 parts. Here, you need S of 5 inches. Here you need S equal 9 inches. And here, you don't need stirrups. Okay? I know this distance is 37 inches. Now I need to know this distance. At what point should I, stop my stirrups at all? How can I find that distance? Again, the same equation. Okay? Put the shear equal to 16.009 not pounds, kilos. K in that equation. Okay? So, have the shear 6.009 K equal to 100.8 K minus 14.4 X. So therefore, X is equal to let me see here, this is 70, it's actually in feet, the equation will give you that this number in feet, so 5.89 feet multiplying by 12, that's going to be 70.66 inches. So that distance from the beginning is 70.66 inches to that point. Subtracting those two values, you can know this distance, 70.66 minus 36.7. That's the distance where you need number 9 stirrups, and then here you don't use stirrups. Okay? So, is that, yes?
So the stirrups don't really, I guess, they don't really affect the strength against like bending moment.
The stirrups, they don't have an effect yet on the strength for the bending moment. But you know, if you use the non-conservative equation for finding CVC, okay, the strength of the concrete depends on the strength or the bending moment, okay, because you have this you have a term that has the moment, okay, if you use the non-conservative equation, okay, but we're not using that here. So, is that the design? Okay, the thing is, you have those spacings, okay, that you have to provide, okay? So you have to provide 5 inches of spacing here. So how many stirrups you're going to provide here? How many stirrups you're going to provide here, okay? So actually you won't be able just to put it here. So let's see how we're going to arrange our stirrups, okay? So my beam looks like this. This is our beam. It's not mine, it's ours. I didn't buy it. Okay? So this is our beam. This is the center of the beam. Okay? This is 84 inches. And then we're going to start providing stirrups. Okay? How will we provide stirrups? Let's use the same colors that we had here. Okay, green, we use green. So let's see here, page what? Green, red, and then purple. That's the purple. Yes. So green. So I'm going to provide stirrups of spacing of 5 inches. Where would I provide the first stirrup? So as a practice, we're going to go 2 inches from the face of the support here. So first one is at 2 inches. Okay? And then I'm going to provide the second one at 5 inches of spacing. So how much is the distance now from the face of the support to the second stirrup? 7. How much is the distance here? You add another 5 inches, it's 12. You add another 1, 17. 22. 27. 32. 37. Right? Now, I don't need to have this 5 inches of spacing. Why? Because this distance now is 37 inches, which is larger than what was required here, right? I needed 36.69, 36.7, right? Now I satisfied this distance. I actually went beyond the 36.7. I went to 37 inches, right? So how many stirrups did we have here? 1, 2, 3, 4, 5, 6, 7, 8, right? So I provided 8 stirrups here. So those are 8 stirrups at 5 inches. Or to write it in a more So 8, number 3 stirrups at 5 inches. So I have 8 stirrups here. Okay? The longitudinal bar looks like this. This is the longitudinal bar here. Okay? And your stirrup definitely is gonna, go to the end here. Okay? And then now I need to provide the number 9 spacing, right? So I'm just going to provide spacing of 9 inches. So how much is the distance now from the beginning of the beam? This is 37 plus 9, 46. 55, 64, 73, right? So right now this is 73. At 70 inches, at the distance of 70 inches, I don't need to provide stirrups anymore. Okay? So I provided till 73, because if I stop here, this is not 70. This is what? 64. So I need to provide that extra one. Okay? So right now, what I had here is 4 at 9 inches. 4 stirrups at 9 inches. And then no stirrups. Okay? So I put 8 stirrups at 5 inches spacing, and then 4 stirrups at 9 inches spacing. And that's it. And that middle part here is going to be empty. I have, this distance was what? 73, right? That is 73 inches. And then over here, I have 11 inches right in the middle with no stirrups. And definitely this is symmetric. So you'll still have another 11 inches here with no stirrups, and then this 4 number 9 bars, and then 8 at 5 inches spacing. Okay? Any question? Okay. If you read through the slides, okay, there were many options that were, tested, okay? We used a spacing of 9 inches. You will find the values, okay? If you use different spacings, 6 inches, 7, 8, 10, and 11.25 inches of spacing, okay? You will find the values, the distances for that, okay? Any question? Okay, so now let's go ahead and solve another example here. We're going to solve example 8.5. Okay? Example 8.5 is the same problem that we just solved. Okay? But I'm asking you to change the loading to make use of the influence line. Apply the load so that the shear is maximized at the different points. Okay? So resolve. So here in example 8.5, resolve example 8.3 that we just solved right now. Okay? With placing the live load so that the shear is maximized at the center of the beam. Okay? So now, I have my beam like this. This is 14 feet, right? I have a dead load. How much was the dead load? I have 1.2 multiplied by the dead load, right? So 1.2 multiplied by the dead load is 4, so 4.8K. And I have the life load. I need to put the life load, okay? If I put the life load everywhere, what would that result in? It would result that the shear here is going to be maximized, okay? But if you put the life load just on the middle of the beam, the shear in the middle of the beam is going to be maximized. How can I find this? Okay, how did I know those pieces of information that I just told you? Okay, so let's say this is point A, this is point B, this is point C. So to maximize the shear at point A, let's draw the influence line for the shear at point A. Okay? The influence line for VA. The influence line for VA, okay, would look like this. 1 and 0 here. So you actually need to maximize the shear at point A, apply the load everywhere. Which we just did in the previous problem, okay? So therefore, V ultimate at point A is 100.8K. That's the maximum shear that can happen at point A, which what we got from the previous problem, 100.8K, okay? To maximize the shear at point C, at the center of the beam, I need to draw the influence line for the shear at the center of the beam. This is point C. So draw the influence line for VC. Drawing the influence line for VC, it will look like this. 0.5 here, and 0.5 here. Negative here and positive here. So to maximize the shear, you have to apply the life load here. On the positive area of the influence line. So I'm just going to apply my life load here. Not only the life load, it's the life load multiplied by 1.6, the load factor. The load factor, 1.6. So right now, let's do this, okay? Where is that? Okay. So the loading that I'm going to have now, I'm going to have the dead load. You cannot avoid the dead load. You have 1.2 multiplied by 4, okay, kibs per foot. And right on the middle of the beam, that part, you have 1.6 times 6 kibs per foot. And now just solve, okay, for the reactions. So this is a structural analysis problem. I'm not going to go through it. You should be an expert in solving a beam like this. The reaction here is going to be 50.4 K, and the reaction here is going to be 84 K. Okay? So the shear right in the middle of the beam, okay? If you draw the shear force diagram, it's going to be 50.4, and then it's going to go like this. $50.4. Okay. This is, yeah, it's going to go like this, and then the slope is going to increase. You have difference in slope here because the W changes. So the shear here right in the middle, so V ultimate max at C is going to be equal 50.4 minus 7 times 4.8 kips per foot. So that is equal to 16.8 K. So 16.8 K. That's the shear right in the middle. Okay, that's the maximum shear that can happen right in the middle of the beam. When you apply the load here, the maximum shear is going to be 16.8 right in the middle of the beam. Okay? Now, I'm not going to solve this problem right to the end, okay? But combining the two cases of loading, okay? Applying the load over the entire beam, how much is the shear here? It was 100.8. And it was how much at the middle? 0, okay? So let's say this is case 1, okay? And this is case 2. So let's draw them all together, just from point A to point C. This is the center of the beam here, not the entire beam. Case 1 looks like this. 100.8 K. Case 2 looks like this. 50.4 and 16.8 K here. Okay? This is case 1 and case 2. So should you design it for case 1 or case 2? When you design this beam?
2.
1 gives you larger value. We did this in structural analysis 1. Do you remember I asked you to draw something called what? The envelope of all cases, right? What's the envelope? The envelope is the maximum value that you get from all cases of loading. So in this part, you should design it for case 1. In this part, because this part gives you maximum, more shear than in case 1, so in this part you design it for case 2, because the shear is higher, right? Okay? Is there any other cases that you should consider? What is the maximum shear at this point? You should apply the load here, right? You should draw the influence line for the shear here, okay? If you do this, okay, you will find that actually you get the envelope of all those cases, it will be something like this. So you design this for the envelope of those of all loading cases. So this green line, okay, is the envelope of all load cases. And that's what you should use for your design. I'm not going to use this line. I'm not going to use this red line. I'm going to use this green line for my design. And then you design it as we did in the previous problem. Okay? Any question? You're going to use this for design. Use for design. If you have any question with this one, just stop by my office. I will be happy to answer any question that you have. Okay, so thank you a lot and see you on Monday.